Hello students, in today's lecture we are going to start the introduction to quantum mechanics and we will start studying from the wave-particle duality. The learning outcome of this lecture will be that you will be able to explain the wave properties of light and the electromagnetic spectrum. Let us first have the recap of the previous lecture. We have studied that atom is not the most basic constituent of matter because we can divide it into at least an electron and the nucleus. Electron was discovered by J.J. Thomson during a gas discharge tube experiment where he was trying to understand the nature of this discharge, where the negative particle as an electron was discovered. And this gave rise to the plum pudding model of the atom. Later on, nucleus was discovered by Rutherford during experimentation on the radioactive radium bromide while studying the alpha particles. Discovery of nucleus gave rise to the Rutherford model of an atom with nucleus in the center and electrons surrounding it. We studied that what force could be responsible for holding the electron and the positively charged nucleus together in the atom to make it stable. And we concluded that classical mechanics and the Coulomb force fails to explain the structure of atom and the stability of atom. We said that classical mechanics cannot explain the structure of atom and we will need a new kind of mechanics, that is the quantum mechanics, to explain the structure of atom. So the study of the quantum mechanics basically started with the concept of wave-particle duality, and specifically the wave-particle duality of light and matter. In the late 1800s and early 1900s, there began to be made some observations that seemed to suggest that maybe its boundary between matter and its particle-like behavior and light and its wave-like behavior wasn't so rigid at all. Radiation or light exhibits both wave-like behavior and particle-like behavior, and it depends on the kind of experiment that which one of these properties we will see, and that consequently matter also exhibits both particle-like behavior and the wave-like behavior. So the quantum mechanics is basically based on the wave-particle duality of light and the wave-particle duality of matter. So we are going to first understand that what is the wave-particle duality. To understand the wave-particle duality of waves, let us see that what is a wave. In the case of water waves, we have the periodic variation of height of water. So waves are basically defined as the periodic variation of some quantity. Like in the case of water waves, we see the periodic variation in the height of water. At some points, the height of the water is lower, and at other points, the height of the water is high. And also then there are some average points where the water height is average. Then there are sound waves. So what are sound waves? Sound wave is the periodic variation of the density of air, as you can see here on the left side. At some points the density of the air is high and at other points it is lower. And then there are some average points where the density is average. So if we draw it in this wave-like form, we see that at this point the density of air is high and at this point the density is low, and the average point is represented by this zero line. So the higher density above this point will be termed as the positive amplitude of the wave, and the higher intensity below this average point will be called as the negative intensity of this wave. So what is light? Light is a periodic variation of electric field. So we first need to understand what is the electric field. For this, suppose that I have two parallel plates like these, and I am going to put a negative potential on this one plate and the positive potential on this plate at the bottom. Now what is operating between these two plates, the negatively charged plate and the positively charged plate, is the Coulomb's interaction that we have studied in the last lecture, that the force between positive charges and the negative charges is the Coulomb force of attraction. Then what will be the electric field? The electric field is the space through which the Coulomb force is operating. So electric field can be defined as a space through which the Coulomb force is basically operating. Now let's suppose if I put a positive charge in between these two plates, then because this is a positive charge, this positive charge will be attracted towards this negative plate. Now if I turn the geometry around, that is, I make the top plate as a positively charged plate and the bottom plate as a negatively charged plate, we will see the same positive charge will now drift toward the negative plate but in the opposite direction. So this shows that this electric field, it not only has a magnitude but it also has the direction. Its magnitude depends on the amount of the positive charge on plate and amount of the negative charge on the plate, and its direction depends on the side on which we have placed the positive plate and the negative plates. So electric field has not only magnitude but it also has the direction, and that is what is represented here in this diagram in the form of wave. Here the magnitude of the electric field is maximum, here it is average, and in the other side it is again maximum, but it is maximum in the opposite direction. So this represents the direction of the electric field and the magnitude is represented by height of this wave. So this point is considered as a 0 point, and the maximum amplitude on the top side is the positive amplitude and the maximum amplitude on the bottom side is the negative amplitude compared to this 0 point. For the waves, the distance between any two of these amplitude, the positive amplitudes, which are also called as the crests, this distance is called as the lambda. And similarly, the distance between these two negative amplitudes is also called as the lambda. So this is the wavelength of any wave, particularly the light wave. So, but not only the light, or we call as the electromagnetic radiation, it is not only the periodic variation of electric field or magnetic field, but light is also the periodic variation of time. That is, light propagates, it moves a certain distance in a certain time. The time it takes to move one wavelength is called as a period. The period is represented by t. We can also characterize the period by the frequency of the wave. That frequency nu is equal to 1 by t, or you can say that time period is inversely proportional to the frequency of the wave. So it is actually, if I were sitting at some point, let's suppose x is equal to 0, and I am watching this wave coming by me, then the frequency is the number of times that this maxima passes by me per second, or the number of times this minima passes by me per second. That will be the frequency of the wave. Then there is another term which is called as the speed of the light. So what is the speed? Speed is usually the distance traveled per unit time, but in the case of waves, the distance is represented by lambda. So the speed of the light or the speed of the electromagnetic radiation is distance d divided by time, where distance can be replaced by the lambda and time period can be replaced by 1 by nu. So here we get c is equal to lambda divided by 1 by nu, or we get c is equal to lambda into nu, where nu is the frequency of the light. It is important to note that all electromagnetic radiation have a constant speed c, which is equal to 3 into 10 raised to the power 8 meter per second. And we will see that how they have all the constant speed. Some light or some electromagnetic radiation have higher wavelength, but they have the lower frequency. The others have higher frequency, but they have the lower wavelength. And that's why this term, the c, that is the speed of electromagnetic radiation, it remains constant. So the light waves are of different types, and generally they are called as the electromagnetic radiations. The different kind of electromagnetic radiations can be represented by the electromagnetic spectrum. The light that we commonly see is called as the white light, that is coming from the sun. It has a wavelength that ranges from 400 to 700 nanometer, and this is the colored light. Different colors of the light, they come under the range of this wavelength, that is 400 to 700 nanometer. Then the other light or another electromagnetic radiation that may have the lower wavelength, like this on the left side, the wavelength is decreasing, and we have different kind of radiation like ultraviolet, X-rays and the gamma rays. The gamma rays has the lowest wavelength, and when the wavelength is lower, that is the distance between these two maximas is getting lower, then the frequency is higher, and when the frequency is higher, the energy is higher. So it means on this left side of the visible light, the radiations are having the high energy. On the other side, on the right side of the visible light, we are seeing that the wavelength is getting bigger and bigger. That is, the distance between these two maximas is getting higher and higher. When the wavelength is getting higher, the frequency is getting lower. And therefore, these radiations, they have lower energy as compared to the visible light. The wavelength of light, it determines the properties of the light or properties of the electromagnetic radiation. For example, the UV visible light, the visible light and a small part of the UV radiation, when they are absorbed by the molecules, then what happens? The electrons in those molecules or atoms, they are excited. By absorbing this light, the electrons get excited, but the excited electrons have to come back to the ground state. When it comes back to the ground state, it emits the same amount of energy. Now this is the light we see when the electrons emit energy in the fluorescent bulbs. And this process of emitting the energy or emitting the light in the form of visible light is called as fluorescence or phosphorescence. When infrared light, that is on the right side, having the lower energy than visible light, it is absorbed by molecules. What happens? The molecules start vibrating. For example, as you can see here, the molecule is vibrating. If you can see this animation, the molecules bonds are vibrating. When the microwave radiation, which have even lower energy, they are absorbed, they cause the molecules to rotate. If you can see this animation, you will see that the molecule is rotating. So you see that the properties of these electromagnetic radiation, they depend upon the wavelength and consequently the frequency of the light. X-rays have higher energy, they are used in the X-rays. Gamma rays have the highest energy and they are emitted during some nuclear reactions. So summarizing today's lecture, we have studied introduction of quantum mechanics by starting with the concept of wave-particle duality. Waves are some periodic variation of any quantity, such as water waves are the periodic variation of height of the water, and light waves are the periodic variation of the electric field. Light waves have both the magnitude and direction. Waves have properties like the time period, wavelength, and the speed. The speed of all electromagnetic radiation is constant, that is 3 into 10 to the power 8 meter per second. And the properties of the electromagnetic radiation, they depend upon their wavelength and frequency.